Hello everyone, I hope you all are doing great. We heartily welcome you all to our YouTube channel cadcaemaster. If you enjoy what you see, hit the subscribe button and turn on the notifications so you never miss an upload. So in this session I'll be taking you through the CA basics. So when it comes to CA basics, today I'll be covering the model, that is frequency analysis. So you could see the agenda. I'll be taking through the introduction of it, and then I'll cover what exactly the natural frequency, how the eigenvalue, eigenvector affects on this, and then resonance, vibration, and related equations of the modal analysis. Okay. Let's get started with this. Let me just activate the pointer, guys. So this is all about the basics. So I'll simply try to go through it, and please try to grab whatever the important points are here. So very important, very crucial points are here. Okay. So when it comes to modal analysis, this is the process, okay, which identify this structures, natural frequencies, and the corresponding modes. Okay. So this is very important. So we get the output as a natural frequency value as well as the corresponding modes. So why this is needed? To understand the dynamic behavior of the structure, so which will help us to prevent the resonance that might lead us to the failure of the structure. Okay, very important point. So when it comes to the key concepts in the modal analysis, the first one is the natural frequency. We call it as a resonant frequency as well. So let's say if I take the tuning fork into account, approximately 450 Hz is the natural frequency of the tuning fork. And if we have another tuning fork which has the same natural frequency, or if you force another tuning fork to exactly the 450 Hz, they both start resonating. Okay, that video I had already seen, guys. If you haven't seen it, please go to YouTube and try to check these videos, how the resonance of the tuning fork, then you'll understand the concept behind it. Yeah, very important thing. So you could see the definition of it here is the frequencies at which a structure vibrates most easily or naturally when excited. So yeah, so this is the definition of the natural frequency. So next one is the mode shape. So why we need this mode shape? So in short, this mode shape describes us the how the structure deforms. In short, how it is going to vibrate when it comes to the practical scenario. Okay. So let's say if I take any of the component, it has certain pattern, so it will vibrate, right? Let's say if I consider the tuning fork again, so the vibration of the tuning fork along the y-axis is natural, right? So depending upon that tendency of the vibration, we extract the natural frequency. Yeah. So this is the importance of it. So how exactly or in what way the structure deforms or vibrates, it shows through the mode shapes. Now the next point is the damping. So this is the measure of the loss of vibrating system. Okay, it's damping in the sense it is just we are going to again, just you can consider a tuning fork itself. So if you hit a tuning fork, it will vibrate for a certain time and then it will come back to the equilibrium state or normal state, right? Because of the damping. So you can hold it by holding it, or else the vacuum, whatever we have, the air, it creates the damping for this, or even the wherever you are going to hold it. So that also might cause the damping. Okay, so a lot of dampings are there, damping factors are also there, we need to consider in short. Okay, so in short, rate at which the vibration decreases over time. Okay, yeah. Well, the next one is the types of modal analysis. So one is when it comes to the theoretical, so we just try to calculate it with respect to mathematical models, and predict the natural frequency of the model as well as the mode shapes. Okay, and then when it comes to experimental model analysis, so we just try to measure the dynamic characteristics of the structure by applying the vibrations and recording the response with sensors. So these are the laboratories which we have it. There we test the models. Let's say any of the components we take it, and then we'll try to extract these values. This is also important to define a set of standards. Right, so everyone has the reference, right? The validations that will be extracted from this experimental method. Yeah. And then the operational model analysis, so where we try to extract the natural frequencies and modes by using the data collected during the normal operation of a structure without an external excitation, using the software or whatever it is. Yeah. Well, when it comes to the purpose and application of the model analysis, so you could see the first one is the design and optimization. So what exactly it does is it will try to identify the potential issues with the vibration during the design phase and the finding solution design phase. Okay. Okay, while designing the components, let's say I have a assembly structure where I am going to mount an engine on the mounting structure. So I'll be using the fasteners, right? So in that design, if I see the fasteners has the natural frequency near, like, which is approximately equivalent to the engine, so definitely resonance will happen, and then the failure will happen, right? So this is just a simple example, so you can even consider a lot of things. So this is what it is. So while designing itself, we try to extract the natural frequencies of the components and try to check the nearby components, whether it is lying within the range or it is exactly matching to the base model, and then we try to reduce the frequencies by adding the material or removing the material, just trying to change the stiffness in short. Yeah, fine. The next one is the preventing resonance, very important factor. Okay, so what exactly it is? Avoid the excitation frequencies that coincides with the natural frequencies, which can lead to a catastrophic failure in short. Yeah, that is what we are trying to do here also. So let's say if the fastener, the earlier example what I gave now, the fastener is having the relative frequency approximately matching to the engine. So what we could do is we can increase the width and height of the fastener. By that we can add the material, and in short we are going to increase the stiffness, and then in short the frequency increases, then we can avoid the resonance. Next one, the validation of models. So when it comes to the comparison, so we take the base model and then reference model and then the optimized modeler or the working model. We try to compare the results, right? In that case we use the model analysis for the comparison of the results. Yes, this is a very important background behind the model analysis and the frequency analysis, so I hope you guys got it. So next thing is when it comes to model analysis, we have the free analysis. One is the forced model analysis, so where we're gonna add the stress additional, like we are going to define, like we force the model for the load cases, and then we extract the mode shapes. Yeah. So now we'll consider on free. What exactly it does is so it will be free, and there won't be any boundary conditions for this. So no loads or no contacts or whatever it is. Yeah. So now if you have it in a vacuum, so definitely that component will have the 6 degrees of freedom. Theoretically, the first 6 natural frequencies should be 0 when it comes to the free analysis. Whatever you do, it should be. So yeah, so that we can even see in the later sessions. Next one is the angular frequency. When it comes to angular frequency, is square root of stiffness matrix divided by mass matrix, K by M. We can say it is natural frequency is the omega n, depends upon the 2 factors, the mass and stiffness. Yeah, so to change the natural frequency we need to alter the mass and the stiffness both. So this is what the relation shows. If it is the frequency, directly proportional to stiffness increases, the frequency also increases. If frequency increases, means if you want to increase the frequency, you need to reduce the mass. Okay, here it is written natural frequency. When it comes to increase in the stiffness, increase in natural frequency also. Yeah. So when it mass is increased, decrease in the natural frequency. So if we add the mass, so it will, yeah, the stiffness will definitely decrease. Well, next one is the free vibration equation. So when it comes to vibration equation, we have the motion equation. That is m into u double dot plus c u dot plus k u, which is equal to 0, where c, in the sense damping, we consider it as 0 generally. Yeah, so we have the mu double dot and ku, in short m x double dot kx in short. Okay, now this formula we are going to take it further and derive the angular frequency, that is frequency relation. I'll take you through that. Yeah, this is a slide. So that is what I told, mu double dot plus cu dot plus k, which is equal to f of t load. So when it comes to the modal analysis, we are not going to consider the damping, so we keep it as constant 0. We remove it, and then we have the mu double dot plus ku, which is equal to 0. Now how do we convert this equation for the modal analysis? So when it comes to the frequency, we measure in the terms of hertz, and then when it comes to that, so we already had seen this kind of zigzag, right? So this is a measurement of the how this is practically defined, the frequencies. If you have the damping, then it slowly reduces its amplitude. Okay, now how we can get the equation? So when it comes to displacement in terms of the angular displacement, so you could see when it comes to the peak, we have the amplitude. This is the phi is the angle we can consider. Okay, now when it comes to this one, so if you consider the sinusoidal wavy movement, so we have the equation displacement is equal to a sine omega t plus phi, where omega is the angular frequency, t is the time, and then this is the angle. Okay, so when it comes to t, this is 2 phi by omega. So time period is equal to inverse of frequency, or frequency equal to 1 by t. Okay, 1 by time period. So this is what it is. So here you could see the equation. So t is equal to 1 by f, and then omega, which is equal to, we had seen the equation, square root of stiffness matrix into mass. And then if I put this here, omega, which is equal to 2 phi into f. Okay, or if you want to extract the frequency, omega by 2 phi. Now this is a small example we have taken. So first one is the equation 50 sine 5000 t is the equation here. Amplitude is the 50 if I take it here, the maximum, and then sine 5000 is the angular omega t. Yeah, 5000 is the yes, it's combined, right? Yeah, 5000 into t. So determine the frequency, and it is the angular frequency, we can say. And then now we have the value, amplitude is this much, angular frequency is this much, so that we can put this equation here. So we know 1 by frequency equal to 1 by t, so that is again equals to omega by 2 phi. So this is the equation, right? Omega by 2 phi. So we have this value, so we put that here, 2 phi, which is equal to 795 hertz. So likewise you can solve it manually. Yeah, just an example, don't take it seriously. Yeah, now we have this a sine omega t plus phi. So where a is the amplitude, we can consider phi is the amplitude here. It is theta is the phase angle, and this is the amplitude, and then this is the angular frequency. And then once we take this one, and we can take the u double dot, if I do it, and then you have this. Yeah, so you can put this one here, this equation is here, and then finally you're gonna have this one. So this is what the final equation is, k minus omega square m phi. Okay, well, in short, this is what the summary here. The natural frequency of the system is inversely proportional to the mass. So as we explained, mass increases, decrease in the frequency. However, natural frequency varies if the mass also varies, in short. Yeah, if stiffness varies, increases, the frequency also increases. So this is how we can just consider these. Well, so this is the background of the equation, so how it has been formed and how we can just extract the final equation from the motion equation. Yes, so for your information, these are the examples. So when it comes to oscillation, so this is also a pendulum, so which is under the natural frequency. We can just consider first oscillation is a swing. Okay, so we are going to manually we are going to add the force on that swings, right? Yeah. Now one more is the spectrograph app captures the natural frequency of your voice or a glass sound when you hit it. Okay, this is the tool which will help us to capture the natural frequency for these. Okay, voice and the glass. When it comes to the devices which are working into resonance is the guitar. So we had seen it, right? And then pneumatic hammers and the soil compactors and the watch. It has the resonance, right? The mobile, the vibration we can see that works on resonance. And then finally we have the microwave ovens. Yeah. So these are all examples for the devices which work in resonance, so which fail in resonance. The example is tuning fork. If another tuning fork has the 440 Hz, then it will definitely fail. And then the fasteners we have it, the washing machine, the pleats and the boilers. Yeah. The examples, so examples of the destruction when it comes to resonance is the Tacoma Bridge. Everyone knows about this one. So it broke at 40 miles per hour wind. And then one more example is the breakdown of the glass with the sound resonance frequency of 450. If you have the sound frequency of 450 Hz, definitely the glass will break. Okay. Yeah. So I think that's all about this session. So we had gone through the introduction to modal analysis. So we had seen the natural frequency, eigenvalue, and the resonance, and the basic equation, how exactly we have extracted it. Yeah, so if you are interested to become a C engineer or a C modeler, please do contact us. We are here to help you guys. Yeah, thank you.
We heartily thank you all for watching this video. If you enjoyed this video, don't forget to hit the subscribe button and give it a thumbs up. Follow us on Facebook, LinkedIn, and Instagram for behind the scenes content and the updates. Stay curious, stay awesome, and see you again in the next video.